Okay, we have an espresso machine here with that funny little arm that sticks out where the steam comes out of. We have a 440 volt supply. The power of the heater is 3.5 kilowatts and we have to choose a suitable fuse. Okay, so let's write down what we know. We know the voltage and kilowatts, that's power. Suitable fuse, well, fuses, as they've shown in the answers, the possible answers, fuses melt above a certain current. So we're looking for current, okay? So what equations do we know that link power, voltage, and current? Well, that would be power is voltage times current, okay? If you don't know that equation, learn it right now. Very important, very useful. Okay, we want to work out current, so rearrange. I is P over V. Stick in the numbers into the calculator. The numbers are power, 3.5. Don't forget it's kilo, you have to turn it into watts. Okay, so 3.5 kilowatts is 3,500 watts. And the voltage is 440. Okay, stick that in your calculator and you get 7.9545. 7.9545, something. We don't need to round it to significant figures or anything because we just have to choose a suitable fuse. It's multiple choice. So here are options. The current is just below 8 amps, so what's a suitable fuse? Well, it's going to be C, isn't it? Because you want a fuse that's just a bit above the normal operating current. If you had a 5 amp fuse, it would melt immediately. Okay, can't have either of those two, and 13 amps, that's just a bit high. 10 is ideal for an operating current of around 8 amps. So the answer is C. 10 amps, 10 amp fuse. Good, okay. Next one, this thing. We're told that the specific heat capacity of water is that. And the question is, show that it takes the heater about 90 seconds to raise the temperature of 1 kilogram of water from 18 degrees C to 95 degrees C. Use an equation from the formula sheet. Okay, so, all right, we're operating in pink now, are we? Okay. So, the question, when you boil it down, is this. They've given you the specific heat capacity of water. They've told you we have a kilogram of water, so that's M, the mass of the water. They've told us the temperature goes from 18 to 95, so that means we can work out delta theta, okay? Delta means the difference, delta theta, difference in temperature, from 18 to 95 is 77 degrees C, okay? And we have to work out the time, how long this is going to take. Okay, so again, use this technique. It's good to write down what you know and what you want, okay? So we know C, M, and delta theta, and we want T. So the equation that they're getting at in the formula sheet is the one that links C, M, and delta theta. And it is delta Q is equal to MC delta theta, okay? Q is energy, thermal energy, change in thermal energy or the rise in thermal energy, okay? So, look, we've got C, M, and delta theta. We can work out delta Q straight away. So let's do it. So, therefore, delta Q is, M is 1, C is 4,200, it's already in the correct units, that's fine, times delta theta is 77, it's also in the correct units. You'd never be expected to change from degrees C anyway. Okay, so let's work it out. Delta Q is, stick that in the calculator, and you get 3,234 joules. Okay, great. So we've worked out the energy which the water has gained. But we want time, okay? So we want time. We've now got delta Q, which is the same as energy. I'm going to write that as equal to E, okay? Because they're both energy, and sometimes in the equation I'm about to use, we're going to use E. They're the same thing, okay? They're just energy, okay? And how are we going to get time and energy? Power is the link, okay? They've told us that the power of this thing is 3.5 kilowatts. We also know power. So time, energy and power. Do you know the equation that links those three? Power is energy over time. Okay? Again, if you don't know that equation, learn it now. That's what power is. It's the rate of energy transfer. Rate means divide by time, so energy per unit time. Energy divided by time. Okay, we're looking for T, so rearrange. So T is E over P. Stick in the numbers. Like I said, the energy is the delta Q. That's 400. And the power is 3.5 kilowatts. So convert into watts, 3,500 watts. Have a bit of a cancel there, if you like. So stick that in your calculator. And you get 92.4 seconds. Done. It was a show that question, which means they sort of give you the answer at the end. But like, don't be intimidated by show that questions. Okay, they said show that it takes about 90 seconds, and that's what we've done. So all that means is just do the question as normal, the way we did, and it will, if you've got it correct, the answer you get will be the one that we gave you at the beginning, which in this case was show that it's near to 90 seconds. And it is. Good. Done. Right. This bit. Describe. Here we go. So, describe, in terms of energy, how the arrangement and movement of particles in the steam changes as the steam enters the milk, condenses and cools. 2 marks only. Okay. Right, so let's look at exactly what they're asking. Describe in terms of energy, because we've got to talk about energy, how the arrangement and movement of particles in the steam changes. So energy and arrangement and movement of particles in steam as it condenses and turns into water. Okay, we could say a lot more than 2 marks here, but I'll just list everything that's relevant, okay, which will be more than 2, but okay, you only need 2. Right, I think the first thing to say would be that in steam, the particles are far apart and fast moving. Okay? Next, as they condense into water, their kinetic energy decreases, they move more slowly and they come closer together. Okay? So, as the steam condenses into water, the kinetic energy decreases, they move more slowly, and they come closer together. The particles we're talking about in this case are obviously H2O molecules. That's what water is, right? But steam is just water in the gas phase. Okay. Right, well, we've probably got 2 marks already, maybe, but you never know with mark schemes and examiners. You know, they can be just looking for one annoying little particular thing and you can think you've answered it well and you don't get the 2 marks, which is why I always say more than you think might be necessary, okay? So try and say at least 3 things for a 2 mark question. Okay, so show the examiner what you know. We can say that the particles release latent heat as they condense. Okay, so the rest of this question is going to be involving latent heat a lot. So let's just briefly make sure you know what that is. Okay, latent heat is a slightly strange concept. Steam contains latent heat, okay? It's the heat energy it gained when it turned from water into steam, okay? It's extra heat energy on top of the heat energy it has just from its kinetic energy of movement, okay? As you increase temperature, the particles move faster and the kinetic energy goes up, the thermal energy goes up. But at the moment it turns from water into steam, and this is true of all liquids as they turn into a gas, they gain this extra energy. It's a bit weird, okay, called latent heat. So that heat is released when it turns back from steam into water, okay? So it's why when you get a steam burn on your hand, it's worse than a burn from boiling water. When the steam, if you've ever put your hand over a kettle or something so it's boiling and it hits your arm, when the steam hits your hand, it condenses from steam into water on your hand, and all that latent heat energy it contains is released into your hand. It gives you a really nasty burn. Much worse than if you put your finger into water at 100 degrees C. Okay, so that's just a little bit about latent heat. Okay, right. So they also release latent heat into the, well, they release latent heat into their surroundings as they condense. Good. What else can we say? We can say that in a liquid, so after they've condensed, the particles are touching, but they can flow past each other. Finally, you can also say that in a liquid, after it's condensed again, the intermolecular, in fact the attractive intermolecular forces are stronger. Okay, so in water, like I said, the particles, the water molecules are touching and they can flow past each other, and it's held together as a water because there are stronger attractive forces when it's water holding them together. Even though they can flow past each other, it's still stronger than when it's in the gas phase. Okay, right, that'll do for that one. Let's clean the board. Okay, so this is what's going on in this final question. What we have is some steam, which weighs 0.025 kilograms, 25 grams, and we're shoving it into this milk, which is initially at 5 degrees C. Okay, the steam condenses into water, and as it does that, it releases latent heat, and that heats the milk up. And then that water, which is at 100 degrees C, that then cools to 65 degrees C and transfers its thermal energy into the milk. So it's important to realise that the milk is heated by two processes. That's the key to this question. Okay. Firstly, the milk gets a load of heat from when the steam at 100 degrees C condenses into water at 100 degrees C. It releases a load of latent heat into the milk. Okay, so that's the first thing. The second way is when the water, which is at 100, cools to 65 and transfers its thermal energy to the milk. So those are the two separate ways the milk is heated. Okay, so what we're saying is that the delta Q of the milk, okay, that's the change in energy of the milk. It comes from two places or two processes. The first one is the delta Q of when the steam condenses, so let's call that latent, okay, plus delta Q of this water when it goes from 100 to 65, so delta Q of the water. Okay, great. Now, the question actually says, by considering the transfer of energy from the steam to the milk, calculate the mass of milk that is heated by the steam and hot water. So our aim is this. Our aim is to calculate the mass of this milk. That's our unknown. Okay? Now, what do they tell us? They've told us the specific heat capacity of the milk. We know the delta theta of the milk. It goes from 5 to 65 degrees C. Now here I've written that the temperature of the milk, theta, is somewhere between 5 and 65 degrees C. And it doesn't matter what that temperature is. We only need to know the initial and final. I've written it like that just to show that when the steam condenses into water and releases a latent heat, that heats the milk up a long way, but it doesn't get it all the way to 65 because it's still got to go from 100 to 65 and heat the milk up a bit more. Okay, that's all that means. It's not really important. Point is, the delta theta of the milk is, overall it's 60. Okay? Right, so Cm delta theta, it's definitely wanting us to write down that delta Q, the milk, is mc delta theta. Okay? So, like we talked about, the delta Q of the milk is equal to delta Q from the latent heat plus the delta Q from the water. So we want m, so let's rearrange for m. So therefore, m equals delta Q of the milk divided by C delta theta of the milk. Okay? Now, we know the C of the milk, we know the delta theta of the milk. So we're going to work out delta Q of the milk from this, and therefore we have m, what we want, and we've won. Okay? So we know that, we just need to know that. So we go over here, like we talked about, delta Q of the milk comes from two processes. Let's work these out. Delta Q from the latent heat. Right, well, this formula is in your formula sheet at the end of the paper, and delta Q of latent heat is quite simply m times L, where m is the mass of the steam, okay, 0.025 kilograms, and L is the specific latent heat of condensation, which they've told us is that, okay? Plus delta Q of the water, same formula. Delta Q of the water is mc delta theta of the water. mc delta theta of the water. Okay, right, let's stick in some numbers. ml, mass, is 0.025. They give it to you in the question in grams. Don't forget to convert to kilograms, very important, okay? Easy way to make an error. L is 2260. Again, kilojoules per kilogram. You need it in joules per kilogram, so kilo, right now, it's in joules per kilogram. Like that. Plus this, mc delta theta. Now the mass of the water, it's the same as the mass of the steam, because all that steam, which had that mass, just turns into water, so it's still got the same mass. It's still 0.025. Okay, times C, which is 4,200. It's in the correct units. Times delta theta of the water. It goes from 100 to 65, so delta theta is 35. Okay, stick these in the calculator and you get, right, this one is 56500, 56500. This one is 3675. Okay, let's just pause a second and look at these numbers. The energy you get from latent heat transfer, it's 5 digits, and just from the water is 4 digits. The latent heat is a whole order of magnitude larger than the heat from just from the water cooling, which gives you an idea of how much energy is stored in latent heat. A lot. Okay, which is why, like I talked about before, when you get a steam burn, it's really nasty. There's loads of energy that's released into your hand in a steam burn. Okay, enough talking about burns, let's get on with it. So these two added together is 60175. 60175. Units aren't important yet. I could add units, but we'll do that right at the end. So we now have delta Q of the milk. Brilliant, so we've won. We can calculate our mass because we know these, C and delta theta. So therefore the mass of this milk is delta Q of the milk, 60175, 60175, divided by C of the milk is 3840. It's in the correct units, joules, kilograms and kelvins, times delta theta of the milk is 60 degrees. Okay, stick it in your calculator and you get 0.261176 something something something. Sensible choice of decimal places. I think 2 decimal places. We'll go for 0. That one leaves the 6 alone. 0.26 mass is kilograms. There we go. That is the answer. So, as always, let's do a quick check and see if we've got a sensible answer. If you've made an error with units somewhere, like you've forgotten that was kilojoules, so you didn't add those 3 zeros there, or you left it in grams, so you had just 25 there and there instead of 0.025, something like that, you get a silly answer. If you get something like 200 kilograms, okay? Now, I don't know which Starbucks you've been going to, but they don't make 200 kilogram lattes, right? So 0.26 kilograms of milk, is that a sensible answer? Yes, it is, because roughly milk, like one kilogram will fill a volume of about 1 litre, okay? So that's about 1/4 of a litre. And that seems like a sensible amount to make a latte, right? So it's probably correct. Always do that check at the end. It is correct. Right, good. Well, there you go. That is how to do that question. Now, under exam conditions, that was only a 4-mark question, by the way. That's a lot of work and a difficult question for only 4 marks in an exam. So, let's talk about exam technique. If you come across this question in the exam, well, I mean a question like this, a difficult one, okay, that's more difficult than the number of marks it's allocated. It's disproportionately difficult, okay? Exam technique, leave it to the end of the exam, skip it, okay? Now I know in this specimen paper, this particular question was the last question, okay? So they were being kind, they left the difficult one till the end, but so often they put the really difficult one like this in the middle of the paper, question 5, and you just do the questions in order, 1, 2, 3, 4, 5, and you get bogged down and you waste half an hour trying to solve the difficult question, okay? You must be alert when you come across a difficult question in the exam. Skip it, leave it to the end. Do all the others and come back to it, okay? And use the time that you've got at the end of the exam to try the difficult ones. Yeah, there we go. I think that's everything. We'll leave it there. It's not super difficult though. You can do this, right? I know you can do this. Definitely. Right. We're still not finished. We've got another question to do, haven't we? Right, final question. Give 2 reasons why the actual mass of steam needed to heat the milk from 5 to 65 degrees C is greater than 25 grams. Okay, 2 marks. Right, so this question is getting at heat loss, right? You're shoving this steam into the milk and all the energy in the steam is not going to be transferred to the milk. It's going to go to other places. This always happens, okay? So that's only one thing, right? So how do we get 2 marks out of this? Well, my advice would be, in the exam, if you get asked this kind of question, if you can only think of one way in which heat is lost, well, if you can only think of one answer, okay, which is that heat is lost to the surroundings, it doesn't all go into the milk. But it's a 2-mark question. How to get the 2nd mark? Just split it up into 2 different places in the surroundings which the heat goes to. And those 2 places I can think of are the jug, which the milk is sitting in, and the surrounding air. Okay? And that will probably get you the 2 marks. So, first thing to say is that heat energy from the steam goes into the jug which the milk is in. Okay? And also say heat energy from the steam goes into the surrounding air or the surroundings. Okay? Like I say, that'll probably get you 2 marks. However, you could also say in this case that some steam is likely to escape before condensing. Okay, so that steam will condense somewhere else in the surrounding air or on the espresso machine itself or somewhere else or on the barista's hand. Okay, so you could also say that some steam may escape before condensing. Okay, heat energy from the steam condensing. Yeah, it's important to say that. You're talking about heat energy, the latent heat when it condenses into water. Heat energy from the steam condensing. Good, and that'll get you your 2 marks. Okay, finished.